Welcome to our second tutorial. Today our subject matter is a bit more abstract, so we'll try to go slowly and explain as simply as possible. What is chemistry? The science and study of, some might say, atoms and molecules and how they combine and react. But chemistry doesn't change or create atoms, at least not the nuclei within the center of them. For example, when sodium metal burns, the sodium nuclei comprising 11 protons and 12 neutrons are still the same at the end of the reaction as they were at the start. No change. But as you probably know, atoms are not just made up of protons and neutrons in the nucleus. They also have electrons as well. And in many cases it's the electrons which determine chemical behavior. So we're going to focus in this tutorial and the next one on getting to know electrons a little better. Here's a grain of rice. Let's pretend that this is equivalent to the mass of an electron. The equivalent of a proton is over 1800 times as much mass. So the same as all the rice in the container. So the first important thing is that electrons are really small. And this is key. Because they are incredibly small, they have some very interesting properties. In fact, they don't behave according to the normal laws of physics as we understand them on a macro scale. Objects on a human scale obey the Newtonian laws of physics, but when things get very big it's the laws of relativity which take over. Likewise, when things get very small, down to the scale of electrons, it's a new set of rules called quantum physics which take over. And although it's a good approximation to treat the relatively large nucleus of an atom as if it behaved like a tiny particle, like a pool ball sitting in space, for electrons a lot of the time it's more accurate to think of them as waves. So let's look at waves a bit more. When we mean waves, we don't mean waves traveling through water or like sound through air, but more like what are called standing waves of the electrons sitting in space around the nucleus. Let's look at a real-life wave so you can understand this better. Here's an elastic band set up on a clamp stand with lots of tension in it. Time for some lamp music. The elastic band vibrates when it's plucked at a particular frequency, creating a sound. Let's adjust and increase the tension a bit. And a bit more. The frequency of the wave changes as we change the material. Here's another example. Again, the glass vibrates, creating a tone. But why that tone? How does the glass know that it has to vibrate in that way and form that particular wave? Well, let's look at the string. It's fixed at either end, so there's no way these can move up and down. So there are only certain ways that you can actually draw a wave. Here's the first one. This most simple wave form is called the fundamental. But we can draw others which look like this. These are called harmonics, and what's interesting about them is that you can see that there are places along the length of the string, like the start and end positions, where the string doesn't actually move. These are called nodes. Pretend that the string isn't constrained at the ends and can vibrate in any way at all at any frequency. What's going to happen? Imagine this waveform averaged out over a period of time. The result is going to be that everything cancels out and you're left with no wave. Let's go back to electrons now. Unlike a string which is one-dimensional, an electron is three-dimensional around the nucleus of an atom. If we do some mathematics, we can actually model this and actually see what these waves look like. Here we go. This is a graphical representation of the fundamental waveform for an electron in 3 dimensions. It's like a sphere surrounding the nucleus. Just like the waveform for the string, you can't think of this as the area in which the electron tends to hang out. Now let's look at some harmonics because this is where it gets interesting. Okay, here's the first harmonic wave for the electron. Actually, there are 3 of them which can all exist separately along each of the 3 dimensions. Each one is dumbbell-shaped, and you can see that like the string harmonic wave, there is a node in the center where the electron wave never actually has a presence. Let's look at the next harmonic. Here's the second electron wave harmonic. There are 5 of these which are possible and which can all coexist just like the last set. There are some really interesting shapes with electron density sticking out at angles and a few different nodes present. Here's our first 3 sets of orbitals. There are more, but these are the ones you encountered in normal chemical life. Well, the maths tells us a few more important things. First of all, each of these orbitals can actually hold 2 different electrons. The 2 electrons in one orbital are differentiated by a property which is called spin. It doesn't mean that they are actually spinning, but it's just a term used. The next important thing the maths tells us is that these orbitals contain electrons at different energy levels. If we start to fill up the orbitals, then the filling sequence looks a bit like this. First there is a s-type orbital which is filled with 2 electrons. Then at a slightly higher energy there is another larger s-type orbital which can fill with another 2 electrons. Then a p-type orbital which can fill with 6 electrons. Then another higher level s-type orbital. Then another set of p-type orbitals. Next another s-type. And then our first set of d-type orbitals. Why it happens like this is down to the energy levels, and if you want to find out more you can research it. One more important thing. When sets of these orbitals are filled with electrons, they form what are called shells. Complete shells are very happy and stable systems. Complete orbitals full of electrons are also stable and happy. This is important because orbitals and shells are filled, the electrons become quite unreactive and don't contribute much to the chemistry of an atom. So let's look at sodium metal. The nucleus has 11 protons and so it needs 11 electrons to balance it. Here's how we represented it before. But let's draw a more accurate representation now that we know what the electrons kind of look like. Here are the orbitals that we need to accommodate 11 electrons. So here's what our sodium atom looks like with all of these simultaneously. And of course, inside the center of all these electron clouds but invisible on here, lies the nucleus. Let's look at sodium on our energy diagram that we drew before. Now remember where the shells are. Sodium has got a first shell filled with 2 electrons, a second shell filled with another 8 electrons making 10 in total, and then 1 electron sitting in the s orbital. Like we said before, the filled shells don't contribute much to the chemical properties. It's all down to that single electron sitting in the outermost s orbital. And this is where this model comes in useful. If you know what the electronic configuration of any atom is, you can find out how many electrons are sitting in the partially filled outer orbitals. And from that you can tell a lot about the chemical properties of the atom. In sodium's case, it's got that single electron sitting there. The whole system can be much more stable and happy with a nicely full shell, so what can happen is that it can't lose this electron. By doing this it ends up with a nice stable electronic configuration, but with not enough electrons to balance completely the positive charge of the protons, leaving an overall 1+ charge. This is a sodium ion. And that's what happens when sodium burns in air. It's losing its outer electron, forming a stable configuration. The energy difference in forming that happy low energy configuration is given off as heat. Let's look now at what happens to the oxygen in the air that combines with the sodium. For the moment we'll simplify things and we'll pretend that the oxygen is reacting as atoms rather than molecules. This isn't correct, but it will help us demonstrate the point. Here's our oxygen atom with 8 protons and 8 electrons. And our more accurate representation here. Remember the positions of the full shells? Shell 1 is full up with its 2 electrons already. But shell 2 isn't full. There are only 4 electrons in the p-type orbital, and to have a full shell needs 6. Remember there are 3 p orbitals and each can hold 2 electrons with different spins. So the oxygen atom is 2 electrons short. Well, if an oxygen atom is 2 electrons short of a nice happy stable full shell, then it could in theory lose 6 electrons. But this would be very difficult. Much more easy for it is to gain 2 electrons. By gaining 2 electrons it obtains its stable shell with 6 electrons in the p orbitals. But this leaves the charge unbalanced and with a net -2 charge. This is an oxygen ion, normally known as an oxide ion. So we know that sodium atoms want to lose an electron, and oxygen atoms want to gain 2 electrons. And this explains why sodium and oxygen react together so vigorously. It's a win-win partnership for them both. The resulting compound is sodium oxide. 2 sodium ions and 1 oxide ion. Well, if you've been watching ChemPlayer for a while, you will be very familiar with lots of reactions that we have done which are oxidation and reduction type reactions. Here's just a few examples. The process we just talked about of an atom giving up electrons or receiving them in order to become more stable has another common name in chemistry. Yes, you guessed it. Oxidation and reduction. Oxidation is a loss of electrons. Reduction is a gain in electrons. Note that they do have to happen at the same time because for something to gain an electron something else has to lose it. So in our reaction, sodium gets oxidized and oxygen gets reduced. And likewise, if you can't find a way to reduce sodium ions then you will end up with sodium atoms, i.e. sodium metal. That's all we're going to cover in this video. In the next tutorial we'll look at how electrons form bonds and molecules, and how these then react as a result of electrons. We've only had time to skim the surface of this topic and there's a lot to discover if you head to your favorite search engine and do some research using the topics and terminology we've covered here as a starting point. Here's the key points to check off in your mind. 1. Electrons are three-dimensional waves around the nucleus of an atom, and they form lots of different harmonics and shapes called orbitals. 2. If you fit more electrons around a nucleus, each orbital can take 2 electrons. 3. The different orbitals fill up in the certain sequence which is related to their energy levels. 4. Combinations of these orbitals form what is called shells, and full shells of electrons are highly stable and happy systems. 5. The outer orbitals which are partially filled with electrons are the ones which determine the chemical behavior of an atom. 6. Atoms like to find a way to either lose or gain electrons in order to create a more stable full shell system. 7. The process of losing electrons is called oxidation. The process of gaining electrons is called reduction. And finally, here's a quick glossary of the main terms we use so that you can use them to do your own research. Stay tuned for more reactions and tutorials soon.